Namaskar. So, in today's session we will discuss about the magnetically coupled circuit. So, let us start our discussion about the topic. So, basically the circuits which we have discussed till now were conductively coupled. That means that because of one loop the neighborhood loop was getting affected through current conduction. That means that both of the loops were joined together and current was flowing from one loop to other. Now, in this case we will see when the two loops which may be or may not be connected electrically, but they are coupled together through the magnetic field generated by one of them. So, in those cases when we see those kind of circuit combinations, we call them as magnetically coupled circuit. So, the most common example for this is the transformer, where the electrical device is designed on the basis of the concept of magnetic coupling. Now, it uses magnetically coupled coils to transfer the energy from one circuit to the other. Transformers are the key circuit elements of power system network. Why? Because whenever we have to change the voltage level, that means either you are stepping up or stepping down in the power system network, you need transformers for those cases. So, now let us see first what is the mutual inductance. Now, when two conductors, or you can say when two coils are in a close proximity to each other, the magnetic flux caused by the current in one coil links with the other coil, and thereby it induces the voltage in the second coil, and this particular phenomena is known as mutual inductance. Now, let us first consider single conductor single inductor, where the coil has n number of turns. Now, when the current flows, let us say the current I is flowing through the coil, the magnetic flux phi will be produced around it. So, if you see the figure, the current I is flowing in the inductor and flux phi is generated. So, because of that flux generated, you will have the voltage V induced. Now, how the voltage will be induced? Because if you remember the Faraday's law, it says that the voltage induced in the coil is proportional to the number of turns and the rate of change of magnetic flux. So, how we can write? The induced voltage V is nothing but N d phi by dt. Now, the flux is produced by current I. So, therefore, we can also say that any change in phi is caused by the change in current. So, this particular equation we can rearrange and write like this, that V equal to N d phi by di multiplied by di by dt. Now, this component is nothing but the inductance L. So, we can write V is nothing but L di by dt. So, this particular equation now tells the voltage current relationship for the inductor. Now, this inductance is commonly called as self inductance, because it relates the voltage induced in a coil by time varying current in the same coil. Now, let us consider two coils, and we assume that they have the self inductances L1 and L2, and both coils are placed in a close proximity with each other. Now, if coil 1 has N1 turns and coil 2 has N2 turns, for this particular case, for the sake of simplicity, let us assume that the second inductor carries no current. So, now the magnetic flux phi 1 which will be coming from the coil 1 will have two components. One component that links only the coil 1. So, if you see the magnetic flux generated in this particular coil has phi 1 which is linked to only coil 1, and another component phi 12 which links the second coil also. So, what you can say? You can say the total flux phi 1 is nothing but a combination of phi 11 plus phi 12. Now, as we know that the two coils are physically separated, means they are not electrically connected. So, we can say that they are simply magnetically coupled. Now, since flux phi 1 links coil 1, because the if you see the figure, flux for phi 1, that is phi 11 plus phi 12 is completely linking this particular coil 1. So, what we can write? The voltage induced in coil 1 is nothing but V 1 is equal to N 1 d phi 1 by dt, or you can write N 1 d phi 1 by d I 1 into d I 1 by dt. Now, this will be your inductance L 1. So, you can write V 1 is nothing but L 1 d I 1 by dt. So, what is I 1? I 1 is the current in the coil 1 and L 1 is the self inductance of coil 1. Now, the second part, basically the phi 12 part of the total flux phi 1 only links the coil 2. So, the voltage induced in coil 2 because of the flux portion of the flux caused by current I 1, that is phi 12, what would be the value of induced voltage in the coil. So, in that case what we can write, V 2 is nothing but N 2 d phi 12 by dt, or you can write N 2 d phi 12 by d I 1 into d I 1 by dt. So, this particular section of the expression we represented as M21, and then this particular equation will be V 2 is equal to M21 d I 1 by dt. What is M21? M21 will be the mutual inductance of coil 2 with respect to coil 1. Now, the subscript, that is 21 written in M21, it indicates that the inductance relates to voltage induced in coil 2 due to the current flowing in coil 1. Now, let us consider the current I 2 flows through coil 2. So, if you see the figure in the slide, now I 2 is the current source connected to the coil 2. The flux phi 2 which is generated by the current coil I 2 will again have the two components. One component phi 22 which will link only the second coil, while the phi 21 will link both of the coils. So, you can say phi 2 is nothing but phi 21 plus phi 22. Now, again as was in the case of coil 1, in this case also you will see phi 2 will link completely to the coil 2. So, what we can write? We can write V 2 is nothing but N 2, N 2 is number of turns in the second coil, d phi 2 by dt, or if we rearrange it, it can be written as N 2 into d phi 2 by d I 2 into d I 2 by dt. Now, this particular portion you can write it as L 2. So, your V 2 will be now equal to L 2 d I 2 by dt. So, what is I 2? I 2 is the current in coil 2 and L 2 is the self inductance of coil 2. Now, the phi 2 1 part of the flux phi 2 will link the coil 1. So, the voltage induced in coil 1 because of the current flowing in coil 2 can be written as V 1 is equal to N 1 d phi 2 1 by dt, or you can rearrange it like N 1 into d phi 2 1 by d I 2 into d I 2 by dt. So, this will become M 1 2. What is M 1 2? M 1 2 is the mutual inductance of coil 1 with respect to coil 2. So, you can write V 1 is nothing but M 1 2 d I 2 by dt. Now, this mutual inductance is the ability of one inductor to induce voltage across a neighboring inductor. So, this will again be represented, it will be measured in Henrys, or in short you can write as capital H. Now, although the mutual inductance M is always a positive quantity, the voltage, that is mutual voltage represented as M di by dt, may be negative or positive. So, unlike the self induced L di by dt, because L di by dt you can find out the polarity. How? You will determine the polarity by the reference direction of the current and reference polarity of the voltage. So, if you remember, we discussed the passive sign convention in our first week. So, you can use that discussion to find out the polarity in case of you have self induced voltage, that is L di by dt. Now, for the polarity of mutual voltage, that is M di by dt, it is not that easy, because it now involves 4 terminals. So, 2 terminals of coil 1 and 2 terminals of coil 2. So, since we have 4 terminals, we cannot use the passive sign convention directly to find out the polarity of mutual voltage. Now, the choice of correct polarity for M di by dt is made by examining the orientation of the coil, that means the way in which both coils are physically wound, and then applying the Lenz's law along with the right hand rule to find the correct polarity for mutual voltage. Now, since it is not easy to show the construction detail of the coil, that means how both of the coils are physically wound, what we do? We generally use the dot convention for our circuit analysis. So, by this convention, a dot is placed in the circuit at one end of each of the 2 magnetically coupled coils to indicate the direction of the magnetic flux if current enters that dotted terminal of the coil. So, we show when the current enters the dotted terminal of the coil, how the mutual voltage would be oriented. Now, let us understand this particular concept with the help of this figure. Here, if you see, the current I 1 is entering the dot. So, the orientation, if you see, the coil is wound like this. If you place a hand palm in such a way that it is completely curling the side of the coil, like if you place your hand and you curl your fingers like this, the coil is wound. So, you will see when you place hand like this, your thumb will be in this direction. So, this thumb direction will show you how and in what direction your flux is rotating. So, here the current I 1 is going inside, you are getting flux phi 1 2 linking in the clockwise direction to the coil 2. Similarly, in the coil 2, current is entering the dot and the positive polarity of the voltage is where the dot is connected, here also the positive is where the dot is connected. So, when you place the right hand in the similar way as we did in this case, your thumb will be in the downward direction. So, again your phi 2 1 will again link the first coil in the clockwise direction. So, now in this particular case the dots are already placed. So, we will not bother how to place them. The dots are used along with the dot convention to determine the polarity of the mutual voltage. So, we will see how, if this is the condition, how we can determine the induced mutual voltage polarity. Now, let us understand the dot convention first. If a current enters the dotted terminal of one coil, the reference polarity of the mutual voltage in the second coil is positive at the dotted terminal of the second coil. So, if current is entering here, the mutual inductance will have the positive polarity in the dotted side of the terminal. Now, if the current leaves the dotted terminal of one coil, the reference polarity of the mutual voltage in the second coil is negative at the dotted terminal of the coil. So, suppose if the direction of current is opposite and current is flowing from this side, in that case the polarity of the voltage, that is induced mutual voltage, would be like this. So, that means that the second coil, the mutual voltage in the second coil will be negative at the dotted terminal of the second coil. Thus, the reference polarity of the mutual voltage depends upon the reference direction of inducing current and the dots on the coupled coils. So, these two things are important to find out the reference polarity of the mutual voltage. Let us understand this particular phenomena with the help of couple of examples. Let us see this particular figure where the sign of mutual voltage V 2 is determined by the reference polarity for V 2 and the direction of I 1. So, if you see the current I 1 is flowing inside the dot, the reference polarity for V 2 will have positive at the dotted side of the terminal on secondary side, because I 1 enters the dotted terminal of coil 1 and V 2 is positive at the dotted terminal of coil 2, the mutual voltage will be positive m di 1 by dt. Now, in this case, now I 1 is entering the dotted terminal of coil 1, but the V 2 is negative at the dotted terminal of coil 2, because the polarity of V 2 is opposite, the dotted terminal is having the negative. So, the mutual voltage will be minus m d I 1 by dt. Now, similarly, in this case, when the current is flowing in second coil, so the current is flowing as I 2 is flowing in the second coil, that means that I 2 is leaving the dot. So, that means if it is leaving the dot, the value of mutual induced voltage will be negative at the downward terminal and positive at the dotted terminal. Similarly, in case of I 2, when I 2 is exiting the dot, but the voltage polarity at the second will have minus at the dotted terminal, in that case your induced mutual voltage will be m di 2 by dt. Since here you are exiting the dot and the polarity of voltage at the dot is negative, it means that your mutual induced voltage would be m di 2 by dt, which is positive. Now, let us consider the circuit where the coils are electrically connected also. So, if you see that coil L1 is connected to L2 physically as well as magnetically. Now, in this case, if the current is going inside the dot, and in this case again the current is going inside the dot, the total inductance will be the adding connection, that means L1 plus L2 plus 2m will be the total inductance of this arrangement. Similarly, in the second case where current I is entering the dot and here current I is again leaving the dot, that means that the mutual inductance will be in opposite direction and the total inductance will you will get as L1 plus L2 minus of 2m, because this is called opposing connection. Current is going inside the dot from one direction, but exiting the dot from other side. So, now we can say that we know how to determine the polarity of the mutual voltage. Now, let us solve few of the circuits so that we can understand how you can involve the mutual inductance and in our circuit analysis. Let us see this particular figure where we have V1 and V2 two voltages applied across the two coils which are placed nearby. So, these two are magnetically coupled. So, we can use Kirchhoff voltage law to write the equations for both of the meshes. Let us say that the current I1 in this particular mesh is in this direction, I2 is in this direction. So, for coil 1 what we can write, V1 is nothing but I1 R1 plus L1 dI1 by dt because of the coil 1 self inductance, then plus M di2 by dt. Now, here in both of the cases your current is going inside the dot, or reference polarity is positive in both of the sides where the dot is connected. It means that the mutual inductance, mutual voltage which you get because of the magnetic coupling of these two coils will be positive. So, you can write V1 is equal to I1 R1 plus L1 dI1 by dt plus M di2 by dt, or in frequency domain you can write V1 is equal to R1 plus j omega L1 into I1 plus j omega M I2. Now, for the second coil what you can write, V2 is equal to I2 R2 plus L2 di2 by dt plus M di1 by dt, because induced mutual voltage will be of positive polarity in this case also. So, you can write V2 is equal to R2 plus j omega L2 into I2 plus j omega M I1. So, now let us take another example where we consider the circuit as shown in the figure. Here in the first part of the circuit we have voltage V connected, while in the second part we have load, that is ZL connected. So, how we will write the loop equations for both of the legs? Now, let us apply KVL to coil 1. So, for coil 1 it is Z1 plus j omega L1 into I1. Here your mutual voltage is negative. So, you will write minus j omega M I2 because I1 is going inside the dot, here I2 is coming outside the dot, and if it is positive then the mutual voltage will be negative. So, what we will write? We will write V is equal to Z1 j omega L1 into I1 minus j omega M I2. Similarly, for second coil what we can write, there is no voltage source, we will write 0 is equal to ZL plus j omega L2 into I2 minus j omega M I1. So, you can see that in both of the cases how the mutual voltage polarity is changing. Now, let us take one example to calculate the value of I1 and I2 in the circuit. So, in this case we have applied voltage, that is 12 volt angle 0, and in the second coil we have applied 12 ohm as a resistance. We will again use the KVL. Since in this case also I1 is going inside the dot, I2 is coming outside the dot, your polarity for the mutual voltage would be negative. So, we will write minus of J3 into I2 for this and minus J3 into I1 for the second coil. So, for mesh 1 what you can write, minus 12 plus minus J4 plus J5 into I1 minus of J3 into I2 for mutual voltage. So, you get after simplification you get Ji1 minus 3Ji2 is equal to 12. For mesh 2 you can write minus J3I1 plus 12 plus J6I2, and if you simplify you get I1 is equal to 2 minus J4I2. So, what you get, you just put the value of I1 in this first mesh equation and simplify, you get I2 as 2.91 angle 14.04 and I1 is equal to 2 minus J4 I2, that is 13.01 angle minus 49.39. So, using KVL again you can solve the circuits where you see these kind of magnetically coupled coils. So, the important thing which you have to remember is that how you will find out the polarity of mutual voltage. So, with this we can close our today's session where we discussed about the magnetically coupled circuit. We will discuss, we will continue our discussion on the magnetically coupled circuits in the next session also, where we will discuss about the energy stored in the magnetically coupled circuit, and then we will also see the ideal transformer and its various equations. Thank you.